Hello, hello. Does it work?
Yeah, yeah. Okay, thanks everyone. Time for the final session of the day with Davide from Edinburgh, presenting on topologically active polymers. And off we go.
Hi, everyone. So, yeah, before I start, I want to thank the organizer for inviting me. No. I want to actually, genuinely thank the organizers for all their efforts. I was following the organization of this conference a little bit behind the scenes, and you can't imagine how much time and care and love they put into organizing this conference. And so I think we should really thank. Well, okay. If it gets noisy, that's fine. Let's leave it there. It will get noisy. That's fine. So I would really like to thank Yair, Valerio, and Simon for putting this together. I think I had a lot of fun in these 3 days, and maybe in the next session, actually, one thing that I want to say is that it seems like also a nice community to work in, and it would be nice to kind of strengthen this kind of network and connections. And maybe in the next session we can talk a little bit about how to do that in the future. So my talk is going to be a little bit different from what I put in the abstract, because I wasn't really sure what to talk about. So there are a few things that are going on in the lab, and I'll say a few things about kinetoplast, but I also want to talk to you about this machine learning of knots beyond topological invariance, which is something that came up a bit more recently, and we've been thinking about it for a long time. Well, for not so long time. And I want to kind of hear also the opinion of people in the room about this. And so here it goes. Let's get started. I'll just do a little bit of a motivation for what we do, why we do what we do. So one of the things that I was struck when I started to kind of think about genome organization, so how the DNA is organized inside cells, is that we have 2 meters of DNA in each of our cells, and to basically function correctly, this DNA has to be topologically and mechanically reorganized at all times. So there are machineries that do that, right? And this reorganization is pretty smart. So this is an example of a cell division. So in purple is the DNA being separated into replicated and separated into daughter cells. Now, if you wanted to, so imagine that you have headphones or this cable here stuck in your pocket. It will take a long time to disentangle any knots or any topological entanglements that you will find. So in order to separate these cables, these very long threads of very long polymers of DNA, one way would be to chop them, right? But then you will scramble completely the genome, so you don't want to do this. You want to be smarter, and so nature has evolved since the early start, kind of when life appeared, this amazing protein called topoisomerase, which most of us know. And so one realization is that this protein is really essential for life. It's one of the most conserved proteins among where there is life. Basically, there is a kind of form, an homolog of topoisomerase. And what this protein does is basically it's a little scissor and a little glue. So when it finds the topological entanglement, it's able to use a little bit of energy. So the type 2 topoisomerase uses a little bit of energy to kind of allow a strand crossing and then seal the crossing back. And this is a local topological activity. Okay, and if you think about it, I mean, basically, it's almost like saying that life exists because there is a protein that does a strand crossing, which is, if you want to really put it into this, which is quite shocking, to be honest. But anyway, so which means that, I mean, it has to be very important. It is important, right? And beyond important, if I think about chemistry, we heard about a little bit about chemists trying to think about these topological materials. There is no equivalent in synthetic chemistry of something like that. Okay, maybe what presented David Lee comes close, this ratchet. But there is nothing like this that can be done in synthetic chemistry. And so the idea inspired by this, what we want to do is, can we use this topological activity into our materials? So can we actually learn from nature and try to make materials that have these properties of where we insert let's say the energy is not into self-proportion, like Daniela was saying, it's not into self-proportion, but the energy is introduced in the system to change the topology of the system. And that brings a change in the viscoelastic behavior. Okay, right, so topoisomerase is not the only protein that does mechanical and topological manipulation to the DNA. There are also other proteins, restriction enzymes we heard about. Recombinases also are quite interesting, and then SMCs, so these loop extruding proteins, they are quite hot at the moment, and which extrude loops in DNA. And these proteins are typically studied in vivo, where they are in very complex environments, and in vitro instead on a situation in which you have a single piece of DNA tethered typically on a surface, and you look at just one protein, one short piece of DNA, which is quite unrealistic. And so what we want to do is to play a little bit in between these two worlds and say, okay, can we reverse engineer and use these proteins in vitro to, in a dense solution, let's say, of DNA to make topological complex fluids? In some sense, we want to play a little bit with molecular biology, a little bit with topology, a little bit with polymer physics to make a sort of a new form of soft matter. So this is the motivation. The group, so I'm doing this with luckily with a lot of smart people, and what basically the group does is a little bit split into two. We do, well, which is strongly overlapping. But on one side, we look at the DNA topologies, and this is, I will say a few words about the kinetoplast DNA. We look into simulations of DNA knotting and mechanisms on how to simplify and to regulate DNA knotting in vivo. And on the other side, we do rheology. So this is simulations by Yair with oxyDNA model of this DNA nanostar system, where we look at the gel states. And actually, and this connects quite well with what Erika was saying, also Francesco earlier this week, is looking at the topological structures inside these gels. And what Yair has found recently is that there is a link actually between the mechanical properties of these gels and the topological features that you find in these gels, which is quite, it's very interesting actually. And we do a lot of microreology, so similar to what Rai was talking about earlier yesterday, where basically we look at how certain proteins that mechanically change the shape, let's say, or the topology of the DNA, change the viscoelastic properties through microreology, because we don't have the gram scale of DNA yet. We also do a little bit of bulk rheology. But yes, it gets expensive very quickly. Okay, so let's get started with some more serious stuff. So I'll say a few words about kDNA. So just to complement a little bit what Luca said yesterday, I mean, his talk was great and basically covered most of it. There is only a few more points that maybe I want to talk a little bit more about. So kinetoplast, okay, so just as to put into context, is the mitochondrial structure, the genome of this parasite. Trypanosomes. So when you slice the trypanosome, the kinetoplast is packaged into this disc shape structure at the base of the flagellum. If you extract it and you put it on a grid, it looks like this, which is amazing. Actually, Randy Kamian always brags that he's got one of the original pictures from the 1970s in his office about this amazing structure, which is very unusual. And Cozzarelli has worked a lot on this to understand the topology. Alex has made a beautiful paper on the bulk behavior that we heard yesterday. And yes, this is the work by Cozzarelli asking what kind of topology this network has. From my perspective, this is also interesting because it reminds me a lot of the cover of Dejean's book, in the sense that this is also an Olympic gel. So it has some peculiar, kind of unique material properties that we want to understand and potentially mimic. So what we wanted to do first was to understand a little bit better the topology of the structure. So what we did was high-resolution IFM. Let me assemble. And so this is when split on the grid. When put on the grid on the mica, this is almost 10 micron across. We can zoom in into the structures a lot and see these beautiful kind of single rings. Some of them are super coiled, some of them are shape of the Africa, which is quite fitting, given that trypanosomes are actually quite abundant in Africa. And you can actually see these structures, these hub shapes, which we characterized. Luca mentioned them a lot. But one thing that we couldn't really make sense is this from these pictures are great, but you cannot really understand the topology of this structure inside. So even if you zoom in, there is no way like to understand where are the rings. You just don't see the rings in a structure like that. And you don't understand what the crossings, what goes over and what goes under. So what we did was to do some molecular dynamic simulations steered by these AFM results. So what we did was to take let's say, just to set the scene up, let's take a ring that is outside the network. We just take that single ring, we binarize the image, and then we say, okay, that is a ring. That I know that is a ring. I can do a simulation and tune parameters. So I can add some beads in my simulation that represent some kind of sink, some kind of absorbing points where my simulated orange mini circle want to go. Okay, I cool the temperature. I do a quenching kind of exercise, and then I try to find the parameters for which I get the best match between my simulated ring and the AFM image. And then, okay, this is relatively easy to do for just one ring. I get but what I want to really do is in the cap, is inside the kinetoplast. And so I take the AFM image, I transform it into a series of beads that act as sinks, as Gaussian attractive potential with respect to the orange beads, but they don't move. So they're just there to basically to attract the final position. And I let it equilibrate. I use the same potentials, the same parameters that I used for the other simulation. And then after this quenching exercise, what I get is a series of, I do it many times. And what I do is a series of conformations that are now resolved in 3D because I have a little slab. They're not in 2D, they are in a little slab. The rings can pass through each other. And I have a 3D resolved conformations that is compatible with, if I take a 2D projection, that would be exactly the AFM image. So then I can do all sorts of computations in terms of Gauss linking number between different rings, for instance, and I can figure out the topology of the network, and I can figure out the valence, which was the outstanding question that was the Cozzarelli gave. Actually, Cozzarelli gave an answer that was the valence for each minicircle was 3, and indeed we find 3 on average, but there is a bit of a distribution there. Okay, so when we thought about, okay, so this is a 2D network with valence 3. The first thing that you should think about is Maxwell, right? So you should always think about Maxwell, but in particular in this case, because a 2D network with less than basically valence 4, it should be floppy, right? Sub-isostatic. So what we're dealing with is effectively a sub-isostatic floppy network that has 0 energy modes. So there is a nice paper by the Macintosh group in which they show that even collagen networks, sometimes they have this Z equal to 3, so 3 valence nodes, but they still stiffen. And they stiffen, though, with a certain critical strain that is valence dependent. And so we took inspiration from that and said, okay, let's try to calculate the Young modulus using this kind of approximation. And said, okay, so you can take basically the density of minicircles in the network, the stiffness of each minicircle that you can get just from a polymer physics argument of a single minicircle basically being a spring, an entropic spring, the radius of gyration of each minicircle, and then you have this valence minus the critical valence for a certain strain, which we took order 1. Okay, so we're most of us physicists here, so it's fine. So and what we get is something an order of magnitude of 10 to the minus 7 Newton meters, which if you put it into context, sorry, you should. Where is it? Here. Am I missing something? I deleted it by mistake. Oh no, yes. Lipid layers. So to put it in the context, lipid layers have a Young modulus of about 0.1 or 1 Newton meters. So this is 10 to the minus 6 times that. So it's 1,000,000 times softer. And also in terms of bending rigidity, you can basically estimate the bending rigidity by taking the Young modulus multiplied by the thickness squared of the membrane, which you take the radius of gyration of the rings, and you get something that is still also about 3 orders, 1,000 times smaller than lipid bilayers, which is a typical. And so what we got at the conclusion at the end is that, well, potentially this is a hard hypothesis that we got only from the structure, is that the kDNA is an ultra-soft 2D topological material. Okay, so this was done in collaboration with Luca and Case, Decker Lab, and came out recently this year. What is next? So more kDNA, and this is mostly led by Sam, who's got really magic hands in the lab, and especially doing these beautiful AFM pictures. So we're doing partial digestion of kDNA with different restriction enzymes. So we look at how the structure is destroyed and how the topology changes, depending on which restriction enzymes we use, which minicircles we remove from the network. we look at different organisms. So here is T. brucei, which is a different form of trypanosome, versus Critidia fasciculata, which is the one that I was showing you before. So here you can clearly see the nodes and these hubs that also Luca was talking about yesterday. And in T. brucei, it's completely gone. So you don't see that structure anymore. So the hypothesis then would be, by following what also Alex is saying, is that here this thing should not buckle in the bulk. So we're trying to see that as well. And the other thing is, the other question is why there is a difference between these two, and what is the mechanical properties different between the two. And one hypothesis is that how the organism replicates the kDNA. So we think that the answer is probably there. And we're trying to do this mechanical perturbation. So we done it only once. We tried this experiment. And it's difficult to see, but what you should be seeing here is a bead. So it's an optical trap. So this is one bead, this is another bead, and here you see these tiny little blobs. So it should be 1 or 2 kinetoplasts, which we trapped with one optical trap with one bead. And the hope is that we'll be able to bring the other one as well and stretch the kinetoplasts and actually directly measure the mechanical properties, the elasticity of this structure. Okay, so now let's shift gears. So when I talk about this machine learning of knots, it gets a little bit more topological in the sense of more rigorous sense of the term. So hopefully, but if you have questions, ask, please. So I'll try to explain the terms that may not be familiar. So first of all, I want to thank the people who did the work, because this was driven by an excellent student, Joseph, by Filippo, allegedly, and Yair. So I want to thank them first. And they begged me not to put these pictures. And so I want to give also a little bit of context. So knot theory actually, so in some sense, it was born here in Edinburgh. So it's actually quite, in some sense, I feel I should bring it back home. So this is Peter Guthrie Tate, who came up with the first table of knots. And Lord Kelvin in Glasgow, he was using knots to explain elements, atoms, different forms of atoms. And now more recently, Morwen Thistlethwaite and collaborators, they expanded this table of knots from 10 crossing knots, 11 crossing knots, 16 crossing knots. There is 1,700,000 knots. The number goes up exponentially the more knots you have. And recently, actually, I received this. I'm not sure if I can share this, but I received it privately from Cam Millett. But apparently, they got a tabulation up to 20 crossings. Anyone wants to bet how many there are? There are 1,800,000,000,000. I'm not even sure how they managed to do that. But anyway, so the question then is, how do you distinguish them? How do you actually show that they're all different, right? And so what people have developed is this concept of topological invariance. So this is a quantity associated with a curve that should not change if you smoothly deform the curve. So let's take an example. You start from something like that, and then you smoothly deform the contour until you get to the unknot. And so you hope that this kind of topological invariant that you come up with is if you calculate this object on the first configuration or the last configuration, it should give you the same number. Okay, this is the concept of topological invariant. Knot polynomial is a more kind of, it's a type of topological invariant. It's a knot invariant in the form of a polynomial. So Alexander polynomial was the first to be developed in 1928, I think, was proposed, and basically it's quite powerful and in some sense simple. You just basically look at one projection, as Mif was saying. So you take one projection of a knot. It doesn't matter which projection in principle, because you can always kind of do smooth deformations to rearrange. And it should be a topological invariant, depending on, so it doesn't matter on which projection. And you assign, basically you create a sort of a matrix from some rules. So I'm not going to the details of the rules, but the point is that you compute the determinant of this matrix, it gets you a polynomial in T. And this kind of polynomial was used to, for instance, detect the two knots which were in the first Tate table. They're actually the same knot. This is now called the Perko pair. This should be an animation. Yeah. So these animations, I have to say, I haven't done it myself. This is not plot. So this is Rob Sharan So yeah, it's his credit. So then let's start with the questions now. Then, so it's an open problem, and is that it doesn't exist currently. So there are different polynomials that have been developed. There doesn't exist a polynomial that is unambiguous. So so you can always find pairs of knots that share the same polynomial. So this is an example. So you have a square knot, a granny knot, and H20. They are clearly different knots, but you always get the same Alexander polynomial. So here, this is a Conway knot and Kinoshita Terasaka. So these are mutants. These are called mutant knots. And they share the same Alexander, Jones, and Conway polynomials. And actually, the Alexander polynomial is 1, which you guess another knot that has Alexander polynomial 1? The unknot. So this is very disappointing, right? For a mathematician to come out to do all this work to come up with a complicated thing, and then this tells you that is equivalent to the unknots, right? So it's quite disappointing, right? So, and the open problem too is that there doesn't exist a way to determine knot topology from the geometry of the embedding. Okay, so there is a couple of examples here. So one of the famous one is the Ferry-Milnor theorem that states that if you integrate the curvature, so this is a geometric quantity, so you integrate the curvature, along a curve, okay, and you get something that is smaller than 4 pi, then it has to be unknotted. But this doesn't say, for instance, that if you get something greater than 4 pi, it's not knotted, because it could be just the unknot with a lot of curvature. So this is a little bit weak constraint. There is a Thurston geometrization conjecture that says that there is a connection between the knots complement hyperbolic volume, which is something that you compute on the geometric space that you create if you take the S3 and you remove the knot. So you can compute this hyperbolic volume, and it's a topological invariant, but it's from the geometry. And there should be a connection with this algebraic invariance, which is more the Alexander that I was telling you before. But there is a conjecture. There is no proof that this is true, right? So there is nothing linking these two families of invariants. And so the question that I really want to ask in this talk, and hopefully we made a little bit of progress in this direction, I'll try to convince you of that, is that are there geometric signatures that uniquely identify a knot topology? Okay. So let's start from the beginning. So this is where the project started with Joseph. So the idea is to come up with the geometric quantities that we can compute on the knot configuration, which could correlate with the knot position, for instance. So you take a simulated polymer. So this was done LAMPS, very similar to what Christian was in terms of modeling. So it's a kind of Kramer-Gress model with some persistent length. And you can compute the local curvature, you can compute the local density, so you walk along the polymer, and for instance, you compute the local curvature, you compute the local density, how many other beads are within a certain volume. You can compute the 1D writhe that I'm going to define right now. So the 1D writhe we define, so the writhe is basically what also Luca was talking about. And basically what you take segments, and effectively what you do is you take two segments and you look at many different projections effectively. You average over all the possible projections and you get a number. You get how entangled they are. And typically, when you're in the calculation of the writhe, in the Lucas equations, for instance, you integrate over the whole contour. But here in this case, we restrict. So we say you integrate between k minus L to k and k to k plus L. So you get a function that is a function of k, which is where you are along the contour. Okay. And then L is a free parameter that you then optimize. Okay, but these are two consecutive segments. This is why it's a 1D writhe. So if you get something that is plectonymic like that, you get a high value of writhe. Otherwise, if you get something like that, it's a low value of 1D writhe. You can do the same with a 3D. So the 3D writhe. So these are quite important also for later. So this I'm really trying to explain them as well as I can. So the 3D writhe, you can do the same thing. So, but instead now you integrate from k minus L to k plus L, and you integrate over the whole contour in Y. So this means that basically for, let's say that I have segments like that, if I look at this segment and I'm in K, so this is segment K, let's say, then I look at all other contour and integrate all the entanglements that I have with any other segment along the contour. And this gives me a 1D curve. And so these are the types of curve that I get if in this particular conformation, for instance. So the curvature is very noisy. The local density, I get these kind of two peaks, a little bit three. And for the 1D right, I get a 1 peak here, and for the 3D right, I get these 2 peaks. And this dashed line corresponds to this point here, which I don't want to go. I don't want to spend too much time going through under over under, but basically you should imagine that basically when we saw these kind of patterns, it's almost like reflecting where the knot is, and not the knot itself, but the ends of the knot, right? There are some essential crossings. It's almost like it's capturing the essential crossings. And so then we asked, what's the correlation between the maximum of those functions and the position of the knot? So what we did was to use Chimonot, so Luca's software to identify the shortest knotted arc. Lucas and Christian when he was in Christian's lab, and so so this shaded region is where the knot is localized for this particular conformation. For instance, this dashed line here that represents one snapshot, and we have many snapshots in time, right? And for each value of time of the simulation, you can basically compute where is the maximum of the local curvature, and you see this all noisy, of maximum density, maximum 1D right, and maximum 3D right. And what you can see is that it gets better and better at recognizing the boundaries of this shaded region. And in fact, what you can see is that there is a colocalization score, no? So how many times the maximum is actually inside this region, you can count. And what you get is actually that the 3D right has always a higher colocalization score corresponding to the random or other geometric invariants, geometric descriptors. Sorry. Okay. So what I'm trying to convince you is basically that there are some patterns there, right? That we were very naively basically we're extracting only the maximum. But that's not the whole story. We can extract much more, right? So the maximum is just, yeah, okay. It's one information, right? So we extract more. So this is why we used machine learning, right? And we were not the first to think about using machine learning to identify knots. Actually, we have probably the first, as far as I know, Professor Dai, in this paper here they did in 2020, and then also Enzo Orlandini and Marco Baiesi. They did this in this year. But we use a kind of a different way to train the network. And so I'll show you that this makes quite a bit of difference. So again, I'll reiterate this concept one more time because it's quite important. So I have this, let's say that I start with the 5 simplest knots. And then I focus on this value of ride. I can define it in 2 ways. So I'm going to call it a segment-to-segment ride, which is just the integrand of what I showed you before. It depends on the XY position along the contour. I can integrate over Y, and that gives me a segment-to-wall ride, which is just a value of X. And this I'm plotting here, it's a segment-to-wall ride. So this is the same picture that I was showing you before, but confusingly is now turned 90 degrees. And this is just to confuse you. And so on the y-axis is the bead coordinates along the polymer, and on the x-axis is this value of segment to wall right for 3 different knots. Well, this is examples. And then we take 100,000 of these per knot, and then we pass it into a feed-forward neural network. And so we have an input layer that where you pass this information. We have 3 or 4, I can't remember, 4 I think hidden layers, and then we have an output layer that basically tells you which each node represents a class, a knot class, and will have a probability at the end associated to it, and it's a probability that the stuff that you put in is that knot. Okay? So basically, after the training, we have a test set, which is an ensemble of knots. We pick one. We ask the network to identify, and then basically what spits out is the probability here of which knot it is, and we take the maximum to say, okay, that is the knot that was passed. Okay, and just to make things to put things into context, our neural network has below 500,000 trainable parameters. I think ChatGPT has got 1 billion. Just to put things into context. So it's probably more exactly. And so yeah. So it's okay. So it's a relatively small neural network in this context. So it's a relatively simple. Okay. Okay. So let's start then to do stuff with this. So the first thing that you do, you measure the accuracy. The accuracy is basically in the test set. Let's say that you have 10 knots that you pick from the 5 simplest knots. You pass them to the neural network. It has to classify it. Let's say that it classifies 5 right and 5 wrong. You get 50% accuracy. Okay. So by training the network with the XYZ coordinates, so what we can do is just take the XYZ coordinates of the knot and pass that to train the network. We get something between 80 and 90% if we use a recurrent neural network, but okay, this is a different kind of exercise. So this was just to show that we get similar results of what was done before. So we get something around 90%, which is not bad, and then the adjacent kind of, it's a different representation, always based on the distance between beads. So it's almost like XYZ coordinates in some sense. The curvature performs very badly, so you get like a 30% accuracy, which is very bad. And then the density gets better, 1D right is better. The segment to all unsigned right, it's a little bit better, but the ones that stands out is the segment to all right, which gets to 99.99% or something like that. And so this basically, when we pass that feature, it contains more information than the coordinates themselves. So it helps the network identify what is important to recognize the knot topology, which that is what is, I think it's a crucial message here. So if we look at the confusion matrix, and for those who are not familiar, basically the confusion matrix is that basically in the test set, let's say that we pass a 4-1, and we ask how many times it finds actually a 4-1 or a 3-1, or a 5-2, okay? So this is what the confusion matrix is, and what you want is as diagonal as possible, so it means that it doesn't get confused. It's very precise. And so when we do this with the segment to all right, we get a very nice clean diagonal, okay? So this is a key point one. This is STA right is quite powerful. Let's see how far we can push it. Knots with same Alexander polynomial. So we take the granny, square granny, and 820. We do the same exercise, and for the XYZ we get quite a decent result. So it's only 3 class, it's not 5 class. It gets confused between the square and the 820 a little bit. I'm not sure why, but then with the segment to all right, it's quite clean. This is good, but we can do better. More confusingly, the Conway and the Kinoshita-Terasaka. So these are the mutant knots, and this is what we get with the XY. So it gets completely confused between the mutant knots, and reasonably so. But then with the segment to all right, we get again 99.99% accuracy. So apparently we can also identify these two knots that share most of polynomials. And they're very difficult to kind of identify among each other. And so this network is doing an amazing job. So when I was talking with a few mathematicians, they say, okay, this looks too good to be true. So when does it break? And so we tried to break it. So we started with the 5 crossings, 6 crossings, 7 crossing knots, 8 crossing knots, 9 crossing knots, and we have also the 10 crossing knots, which is 250 knots. It's quite a big database of 100,000 conformations per single knot. This is for the 9 crossings you get at the end with the XYZ representation, you get something below 30%. But then we do it with the segment to all right, and you get pretty strong diagonal there with an accuracy of stays up to 85%, which is reasonable. But I was a little bit disappointed by these 2 points here. It looks like it starts to get confused between a 5-1 and a 7-2, which is I'm still not sure why. Okay, so then we looked into that a little bit more. And so what we said is that, okay, so these are the 2 knots, so 5-1 and 7-2. We can do this segment to all right, but we can also do the segment to segment. And in this case, we get, instead of having a one-dimensional function, a curve, we get a heat map. So it's a 2-dimension, it's a function of x and y. So this is a segment x, a segment y. And so if you look at basically this is a projection, this is basically a sum over the rows. Basically, if you sum this, you should get basically the value of the segment to all right. But there is more information here, obviously. These patterns are clearly different. Instead, if you look at the 1D right, the segment to all right, the pattern is kind of similar. You get these peaks. This peak is almost the same. This peak is roughly the same. This one is just shifted. So you might get confused in this sense. But in this sense, they are very different. Right? So we retrain the network using the segment to segment right, and we get back the 99.8% this time with the 7 crossing knots. Right? So then if we go to 9 crossing and 10 crossing knots, so there are this many knots that share the same Alexander polynomial, and there is no way to, you can use other polynomials to tell them apart. But actually, all the mutants that you can imagine then will share the same scheme polynomials, where basically the Jones and the You still have a problem. You still have a problem to identify those, right? So what we did was to basically to monitor the accuracy as we increase the number of classes. And basically, with the XYZ, you get down to 25%, as with the 9 crossing and 9 crossings. The segment to all right, again, you go down to 75%, but here, the network is still training, has been training for 3 weeks, I think, and we got to 94%, and it's still training. And final thing, yeah, and final thing, you can do localization too. So you can actually use kMonot to train the network, to identify the knot, to have a ground truth, to say where the knot is, and to pass the writhe. Now this time, if you use a feed-forward neural network, it just doesn't work. You have to use a recurrent neural network that has some kind of information on the adjacency, on the sequence of the nodes, and you get a very good result. So this is a particularly bad example in which the XYZ and the unsigned right will tell you that this part is still knotted, so the probability of knotting for a certain segment. kMonot will tell you that it's not knotted, this part, and the segment to all, I have to find a better name, segment to all writhe, it tells you that these are knotted. So yeah, this is a very good example in which it works, but we haven't looked too much into this yet. Right, conclusions. So with a relatively simple feed-forward neural network, it seems that we go a long way, especially, this is pretty impressive, in my opinion, just to tell apart mutants that otherwise will be identical with basically virtually all non-polynomials. It seems that this combination of training a neural network with this segment-to-segment writhe contains some kind of new knot polynomial or topological invariant that could be more powerful than the ones that currently exist. But the frustration is that we don't know how to extract it, right? So in some sense, it's embedded in the network. We could just say the weights of the network are trained with this quantity is a new sort of knot polynomial or topological invariant. But we don't, numerically, we know what it is in some sense because we know the weights of the network, of the parameters. But we don't know analytically what it is. Okay, and so this frustration kind of converts into a question to you. If you have new ideas, please share, right? Okay, I think that's it. I want to thank the group, especially, so this group, this work was done mostly, well, the Kinetoplast stuff is driven really by Sam, Joseph, Filippo, and Yair on the machine learning, and also all the other kind of guys in the group doing amazing projects, and the funders, obviously, for giving the money, and for the attention. Thank you.
Thank you very much, Davide. Any questions? Go this way around the room to begin with.
Okay. So something that I missed is which configurations do you test this? Like, because a knot can have many different spatial configurations.
Yeah.
So do you take a bunch of them and test all of them?
We sample statistically uncorrelated conformations. So we have 100,000 of those per each knot. We use 90,000 for the training, and we use 10,000 for another bit for the validation, and then let's say 5,000 for the test.
Okay, good.
They are statistically uncorrelated, unseen conformations.
Very nice stuff. So regarding your T. brucei kinetoplast, yours, did you look at like a Chen-type topology experiment, and did you see the same results?
Good question. No, we haven't tried.
Okay.
Yeah, yes. It's a good point. We should do that.
I'll do Elizabeth and then come back. I'll keep doing Nancy. Yeah. There you go.
So I guess I had a sort of follow-on question to the first one of, like, how did you generate the data sets, and have you tried this on knots that were generated from independently from a different method?
Yeah. So the method is just by doing very long lumps simulations. So you have a Langevin, basically a Langevin simulations. So you evolve stochastically the conformation, preserving the topology. So we use this Kramer grass with affinity bonds that doesn't allow strand crossing. So you start with a topology and you just preserve it all the way through. You can simulate it as long as you like. You generate a data set that is as big as you like. And the persistent length is something that we keep it quite high for the moment. And I think probably one of the reasons for why it works so well is because it's quite large. So it's a persistent length of 10 over 100 beads polymer. But we are reducing it as much as possible as well. So we're testing lower persistent lengths. It just probably take longer to train. And we haven't tried the different data sets. So different ways to
sort of thermal distributions or like
yeah, these are thermal distributions. This is thermally sampled conformational space for fixed topology. Yeah.
Since you say that you are trying to break it, have you tried on pseudoknots?
No, but
That could
what do
be,
you think?
I mean,
So is
well, an easy way would be take one of the knots that is a bit complex, let one part, I mean, just a strand passage, so that it become, I mean, if there's a twist knot, you just need one knot it, and keep the conformation that is as close as possible. If it distinguishes it, then that's very good.
so you'll have a divergence of the ride if you have if the crossing is not well defined.
So it should work. The question is
well,
when you
if
have
it-
more complex knots, perhaps it's not enough.
Okay. Yeah.
That
Yeah,
would be
we-
quite poignant.
Okay. Yeah, I haven't thought about it. Okay.
Yeah, lovely talk. My question is about the kinetoplast optical tweezers. I think you said you did this once.
Yeah.
But what is the size? I mean, what is the size of the kinetoplast that you need to trap them? And then you were going to take two kinetoplasts and bring them together?
No, yeah, that wasn't the yeah, it came out. Yeah, the idea is just trap one. So the size of the kinetoplast in bulk is about between Alex 4 microns, so across maybe something like that. So you can see it actually quite easily under a microscope, and then you just bring a bead close by. There is a trick on how to link, so how to get it attached, and once that you have it, you just pull it.
Okay, so you trap the kinetoplast in one trap and trap a bead in the other.
You have two beads. You trap the kinetoplast with two beads.
Oh, I see. Just like a DNA thing.
Yeah, sure. Yeah, exactly. It's like a lambda DNA stretching experiment, but now this time you have a chainmail instead of just a single piece of DNA.
Yeah, cool.
I really enjoyed your talk. I was wondering, because this seems to be I mean, you left us with an open question about the interpretability, but I'm curious about what you think, because I seem to gather from various people that this is a huge problem and kind of discourages people from using machine learning. So yeah, what do you...
Yeah, so yeah, it's a good question. So what do I think? I think that basically this quantity is I put it there. So the signal to all right could be it's a sort of a thought. In my opinion, basically my idea is basically looking at effectively you're looking at the crossing. So the relationship between two segments. So if you get 0, let's say that they are not entangled, but if they are close by, they can be entangled in one way or the other. So you get the sign, you get how much they are entangled, and so in some sense, it's almost like a Docker code. If you're familiar with that, so basically it's a code with which you can generate different knots, but it doesn't distinguish for chirality, for instance. But here the chirality is introduced by the fact that you can tell the direction of the entanglement, and so this is one way I'm thinking about it. And yeah, that's basically it. I don't have much more actually profound or understanding of this rather than try to find the similarities with what there is already there. It's a little bit difficult.
And what about people? I mean, this is a huge neural network, of course, but what about people that are actually studying kind of the interpretability of neural networks in general?
Yeah, it would be, so we're trying, I'm trying to talk to as many people as possible, because this is our first project, my first project involving neural networks. So it started almost like to try to learn machine learning ourselves, and then it developed into this. So we bumped into this almost like by mistake, and then so the idea is to try to talk with people that do this kind of interpretable. Or the other, yeah, so there is a nice paper in Nature in which they use machine learning to help mathematicians to develop theorems. And in that sense, they use this also to make some kind of connections in knot theory between different topological invariants, and they were looking at the saliency or the importance of certain information to connect different topological invariants. So we might try something like that, but it takes a little bit of thinking. Yeah.
Thank you.
Yeah.
Thank you, Davide, for the talk. So I would like to ask if AFM can distinguish what is undercrossing and overcrossing, and if you can train the AI perhaps to help.
Yeah. So if you are Alice Pine, yes, you can distinguish overcrossing and undercrossing. We are not Alice Pine, and also we're not. Yeah, I don't. Yeah, we're pretty. I think we've done amazing progress in the sense of the high resolution AFM, but. So if you really want to see the over and undercrossing, you have to look at the grooves as well. So you have to really zoom in a very small region. So these are huge structures compared to the mini circles that Alice Pine looks at, and that actually can distinguish the over and under. And that has come up only recently. We thought about machine learning brute force that kinetoplast with rings, and it's not like recognizing a horse in an image. You have to recognize many horses, and they're all entangled with each other. So it's probably, yeah, we never even tried, because I think it's, you'll have to put by hand also how many mini circles you have instead of getting it from the density. So you never seriously tried. We considered it, but never seriously tried.
Okay, thank you.
Thanks, that was really nice. How does it go with links?
Oh, good question. I don't know, so we haven't tried, but Roman wants to try with threadings, so we're probably gonna do that with we don't know. I guess it's next on the list. Yes, if once this is out, yeah, we can extend it to links. Yes.
Yeah, super. That's nice.
I was thinking also, yeah, different kind of other kinds of self-assemblies, like the ones that you were talking about, to identify them, even to classify them.
That makes it interesting.
Anyone else? Maybe one more? No? Okay. I think next are we just starting on the roundtable session next?
Yeah. Thanks.